Okay. This is Chapter 17 in the lecture outline, solubility, product equilibrium. In the course of presenting the sections and chapters on equilibrium, we started with the reactions all being in the gas phase. And so in, say, in chapter 14, we talked about gas phase reaction equilibrium and the Kc expression or Kp expression. And when you have a K value expression, it contains all of the components of the equilibrium, of the reaction. So when in that chapter, when we wrote the equilibrium expression, it was products over the reactants, including the all of them. Let's see. Like that. And chapter 15, 16, we were working with electrolyte ionizations, and the amount of ionization is very low. And weak acids and weak bases is where you would find the K expression. The water that these are dissolved in, let me give you an example here. Acetic acid, for example, really reacts with water to form the carbonium ion plus the acetate ion, like that. All that's in water. But this is only about 1% ionized. And when I say 1% ionized, I mean it's very low relative to the amount of water you have. So these are small numbers. Relative to the solvent, very large number. So what is done in writing the equilibrium expression, I'll write it all out. Would look like that. It would contain the products over the reactants, just like I've been teaching. However, this number is so large compared to what these are. That is, very, very, very small amount of the solvent system is used in this ionization. So it does not pose an error if you assume these are generated and water's not changed. It's so large. It's like taking 1 and subtracting 0.00000001. You still got 1. So this is assumed to be a constant transposed to the equilibrium constant side, and you're left with this. then this part of the equilibrium is redefined as an acid ionization constant, Ka, and consists only of the hydronium ion, the acetate ion, and the acid that it came from, like that. So that's why, as we go through the work we're doing, we just put the acid ionizes to H in whatever the anion is. We don't put the water in there. And then we solve the problems around products over reactants. If it was a Kb, it would just involve the ions, say, of the weak base. But you remember, they're in water. So this is really a KEQ times water, Kb. Its subscript just tells you that the substance we're working with is a weak base. All right. In this chapter, solubility product equilibrium, the same issue exists, but we'll add an extra one to that. I'm going to use silver chloride to illustrate the idea here. Silver chloride, a solid, has what we call a Ksp value of 1.8 times 10 to the minus 10. The K value indicates extent of reaction, in this case, extent of dissolution or dissolving. So in silver chloride, our generalization here is maybe one molecule will ionize and send a couple of ions in. The concentration, just to give you an idea, is in the order of 10 to the minus 5. But when you look at the equation of dissolving in water, you have silver ions and chloride ions present. A salt will ionize 100%. Not all salts, you recall, have equal solubilities, but whatever does dissolve ionizes 100%. So we're talking about a system in which you have placed a quantity of salt. And then you just poured a big bunch of it right down here. Dug it out of a box, you know, like table salt. You pouring it in the water. Well, that salt then begins to ionize. And what does it do? It sends a couple of, it starts sending silvers. See that one? Out into solution. And of course it's 1-to-1 ionization. Can you see that? I'll just use black. There's the chlorine. Right there. So there are only small number of silver ions and a very small number of chloride ions. Watch, this is where I'm getting to. Compared to the massive amount of solid down here. It's almost as if the solid didn't change. in the amount that you send into solution. The water out here is infinitely larger than the amount of ions present. So in this equation, if we wrote KEQ expression including everything, would be silver ions. I'm going to leave all the notations out for a second. And there's your solid. I put that in. And H2O as a liquid. Like that. These two components, silver and chloride, going into solution are in the order of 10 to the minus 5 compared to the infinite amount of salt that didn't dissolve and the infinite amount of solvent, water, that wasn't involved in the ionization. So we assume these to be constant. So when we write the equilibrium expression, we move these over to the equilibrium constant side. And leave the ions on the right side that are dissolved in solution. Like that. This term is redefined as a Ksp number. Still has the same meaning in terms of what does the equilibrium constant mean. Extent of reaction, in this case extent of dissolution, is only in terms of the ions that are delivered into solution. You won't have a denominator in this type of equilibrium expression because the number of ions going into solution is so small that it's considered the massive amount of salt that you drop in is considered unchanged relative to the amount of ions it delivers into solution. So it's considered constant. And the only thing you have to worry with, how much went into solution. Like that. So our equilibrium expressions. Okay. We just looked at silver chloride. We'll do one for silver bromide, just grins. So silver bromide as a solid, you should indicate that it's solid. We'll go into as silver ions aqueous plus bromide ions aqueous, like that. What you're looking at is a 1-to-1 ionization ratio. Yes? Okay, so the Ksp expression for this would be only in terms of the product side, silver ions and bromide ions. Now I'm going to leave off the AQs when I write the expression. Everything's going to be in water anyway. You're not going to get this effect any other salt. All right. Here's another one. Lead iodide. This one ionizes in a 1-to-2 ratio. Aqueous. Like that. When you write the equilibrium expression, when you do not have a 1-to-1, you have to use that as the exponent of the concentration bracket. That is, your Ksp for the lead iodide is lead plus 2 iodide squared, like that. Aluminum chloride Ksp is a 1-to-3, and so it's aluminum chloride Q, like that. This is magnesium arsenate. When it ionizes, goes in solution, it will deliver 3 ions of magnesium into solution. And 2 ions of arsenate. Right there. And its Ksp expression is magnesium raised to the 3rd power, arsenate raised to the 2nd power. So we write the equilibrium expressions in terms of only what's delivered into solution. The water, solvent, and the salt that's left behind that didn't ionize are so infinitely larger than the ion concentrations that they are left out of the K expression, or they're just moved over and not considered. Is determining solubility of a salt. Since we're using silver chloride, I use that a lot. It's pretty straightforward. So this is a 1-to-1 ionization ratio. Silver chloride as a solid delivers silver ions and chloride ions in equal amounts in a 1-to-1 ionization ratio. The Ksp expression for this is silver ions times the chloride ion concentrations, like that. Let's use the horse race scenario issue. Initially, you disregard the silver. You just dump a spoonful of silver chloride into a glass of water, and then it cascades to the bottom, leaves you a layer on the bottom. Very little dissolves. But as you start this problem, you have 0 and 0, just like putting that we've always done in building the ICE, initial change and equilibrium table. We put the horses in the gate and let them put the chemicals in the gate, and then open the gate and let them run. So in this are change and concentrations of equilibrium. In each case, we ignore the salt, the solid salt, because again, it's infinitely larger, and we don't even put the water in there. You don't have to do that. Just put the ions delivered. This is going to go up by X, and this one's going to go up by X as a 1-to-1 reaction ratio. And so at equilibrium, we have X and X. Now, you can look up the Ksp for silver chloride. It's 1.8 times 10 to the minus 10. Bunch of tables, okay? So to determine the solubility, we need to find out what X is. If Ksp number is given, then it's not a problem, because Ksp is equal to silver concentration times chloride concentration. Ksp is 1.8 times 10 to the minus 10, which is equal to X from the silver times X from the chloride, which is X squared. So X, which is the concentration of silver ion going into solution, also equals the chloride, because it's a 1-to-1, is equal to the square root of 1.8 times 10 to the minus 10. It all comes out in moles per liter. So I get 1.34 times 10 to the minus 5 mole per liter in silver ions, and chloride ions. Okay? Lead iodide, if I've got it in here. Yeah, I got it. Has a Ksp value of 6.5 times 10 to the minus 9. Determine its solubility. Well, the solubility of silver chloride could be either the chloride or the silver. But in this one, it's the one that we call the least amount. The lowest concentration is the amount moles per liter delivered into solution. Now, if you have two of them ionized, it's still X will be, you just remember X is always the solubility. This will make more sense as we get next couple of problems. So we look at lead iodide ionizing to lead plus 2I minus. We go through the ice table and at equilibrium ignore your salt. Remember? You don't need that. But this one will deliver X in terms of the lead, but it'll deliver 2X in iodine. It's a 1 to 2 ratio. So when I write the Ksp expression for this, I'm going to have lead times I minus squared. Now, this is not 2I minus. Please check mark that. This is the lead going into solution, iodide going into solution, but it has an order of reaction 2. Then you put the exponent up here. Only time whatever you put in the bracket squares, doubles, is when you put that right there, 2x in there. But you put each letter in individually. Don't go doubling the letters, because that'd be 2 times 2x. That's wrong. Okay, so now X is for lead and 2x is for the iodine, and we need to square that one. And so that would be X times 4x squared, which is 4x cubed equals the Ksp, which is 6.5 times 10 to the minus 9. X is the solubility. X is the lead. So whatever X is, you identified as the amount of lead iodide that was delivered into solution. X is the solubility. So when we solve for X, we have the solubility of lead iodide. And when you do that, it is the cube root of Ksp over 4. Always. On a 1 to 2 or 2 to 1 ionization in pure water, your solubility will always be the cube root of Ksp over 4. So our X now, which is equal to our lead ion concentration, is equal to the cube root of 6.5 times 10 to the minus 9 divided by 4, and that will be in moles per liter. So we get 1.18 times 10 to the minus 3 for X. If you're not familiar with how to use cube roots and fourth roots and fifth roots in expressions like this one right here, you need to pull out your how-to your user manual on your calculator and be sure you know how to deal with it. I don't teach calculator here. I advise, but I use this TI, and that's helped me for as long as I can remember. Let's look at lead hydroxide. It has a Ksp value of 2.5 times 10 to the minus 39. Might as well make it look like a 9. 39. Thank you very much. It's going into solution. 10 to the minus 39 for a K value. Not much, as you would expect. The ionization delivers one mole of lead 3 and 3 moles of hydroxide, like that. So we write our Ksp expression in terms of the product side of this. Ions delivered, raise to third power on the hydroxide. At equilibrium, lead's going to be X and hydroxide is going to be 3X. See, one molecule of lead hydroxide sends out 3 hydroxides and 1 lead. So you can just come down here with X and 3X. That's how much was delivered. But the cube has to be placed on the 3X. And that's equal to Ksp. The solubility is X. Solve for X. Well, I'll go ahead and put this as 27X cubed. Okay. So now X is equal to what? X4. That's sorry, X to the 4th. 1 and 3 is 4. They taught me that a long time ago. Anyway, the 4th root of Ksp over 27 will always be a 1 to 3 ionization. X equals the square root of Ksp will always be a 1 to 1. X equals the Ksp over 4 cube root will be a 1 to 2 or 2 to 1 ionization on your salt, always. Here is a 1 to 3 ionization, it's the 4th root of Ksp over 27. It makes it, it's very consistent. Now this is in pure water. We haven't, solubility product issues have common ions also that you have to take into account. And it won't be these. These are in pure water. So we have the 4th root of 2.5 times 10 to the minus 39 over 27 and moles per liter. So the lead from the Ksp right here is X on, and that's the solubility. It's also the solubility. But hydroxide, we had to take into account 3 moles from the molecule was delivered, and so we tripled that, and so there's your hydroxide concentration, 2.94. You can't read that. Times 10 to the minus 10. Okay. One more. We'll do the lead arsenate then. Okay, so there's your lead arsenate Ksp. So lead arsenate ionizes to 3 moles of lead 2 plus 2 moles ASO4 minus 3. The ionization at equilibrium is 3x and 2x. Now, in the calculation, when you solve for X here, X is the solubility. But you'll have to take the X number that you get, while it is the solubility of the lead arsenate, and triple it for the ions of lead and double it for the ions of arsenate. So we'll take this and substitute this data into, or this variables into Ksp expression, which is lead, that's 2, cubed arsenate squared. And that's 3x cubed 2x squared, 27x cubed times 4x squared, (108x to the 5th) is now our expression for Ksp. And the solubility now, X is the 5th root of Ksp over 108. So if you build up, you can go right on up. So these are, I've given you one of each one that you'll see. There's nothing 1 to 5s or 1 to 6s in those. You won't see that. So you'll see a 1 to 1, a 2 to 1 or 1 to 2, 3 to 1 or 1 to 3, 4 to 1. There's a couple, but not. And then you will see a 2-3 or 3-2 ionization like this. So the solubility of the lead arsenate is this number. That's how much of the compound broke down and went into solution. But it is not the lead concentration, and it is not the arsenate concentration. As you recall, the lead concentration is 3x, 3 times that, and the arsenate is 2 times that. So if you were asked on a question, what's the lead concentration, it would be 3x, which is 3 times 3.26 times 10 to the minus 8 moles per liter. So there's your lead concentration right there. And finally, your arsenate is 2 times that number. Okay. So, to make life easy, you can just learn the expressions if you wish. But please know where they came from. I can ask several questions easily on the ionization equation by itself. So you can go into a text or a table and pick out a Ksp, and formula will help you determine the solubility. Okay. The next problem type is Ksp from solubility. So you're given a solubility of one of the salts and has to back calculate to the Ksp. Okay, solubility of lead iodide is 1.2 times 10 to the minus 3 mole per liter, 25 degrees. You'll find all these problems will give you a temperature. Standard, when you get a table, will be at 25 degrees. But in consideration of changing temperatures and things, salt solubilities will also change. Unless there's a very specific reason for changing temperatures, we'll stay with 25 degrees in this chapter. Now, when we get to thermodynamics, we have an experiment where you warm it and get a new solubility constant. But anyway, that's for something else. Okay, so lead iodide, ionizing to 1 to 2. Giving us a Ksp expression of lead and I squared. Okay. Well, if this is the solubility of lead iodide, it's going to be an X value and the one that has 1 mole delivery. So X is equal to the lead iodide concentration, lead iodide and the lead, which is 1.2 times 10 to the minus 3 molar. The iodide, however, is a 2x to get its molar concentration, so I have to double the 1.2 times 10 to the minus 3. And then we substitute into the Ksp expression and compute the Ksp value. So we come out with 6.9 times 10 to the minus 9th. And if you check the table, that'll be exactly what it is. And table. Now, the issue with these kinds of systems, salt systems, is that they have extremely low solubilities. And as you went through the chemistry course, you were given a solubility table when you did metathesis reactions, and the one that precipitated was the driving force. Nobody ever said anything about how much of the driving force remains in solution. Well, this chapter does. Even with a super small amount going into solution, there are some ions there, and you can determine those. If you have an ion concentration such that it will give you this exact number. Now, what did I say? If this is how much you really have made, physically made in solution, you will not see a precipitate. That's right on the edge. It's saturated solution. You have to go above one of these numbers to actually see it cascade out of solution to precipitate. So this leads us to the next topic, next type of problem, which is predicting solubility or precipitation. Okay, here is the problem. You're given calcium at 0.0025 molar and an oxalate concentration of 1 times 10 to the minus 7 molar. Now, if you pour those, two solutions, you pour the two solutions where those concentrations exist, will you get a precipitant? And the Ksp is that value. Well, to get that, it's the QK issue again. All right? I told you, always list your K values first. And in this case, instead of KCs, you're going to get KSPs. And it's either going to be greater than or equal to or less than a Q value. Now, you can call them QSPs if you want to. like that. So in this issue that we're looking at here, what you're saying is you have a calcium oxalate that's ionizing to deliver calcium ions and oxalate ions like that. Well, the concentrations mixed equal what they give you up here. So they're not telling you this is the saturation point. They're asking you if the precipitant is going to form. Is this above, below, and over the Ksp number? So here we have 2.5 times 10 to the minus 3 molar for the calcium, and for the oxalate it's 1 times 10 to the minus 7 molar. So we can calculate the Ksp to equal, that's a 1-to-1 ionization between those two. So it's calcium, C2O4, 2 minus, and that's 2 point, well, I better come down here, get some more room. 2.5 times 10 to the minus 2, and 1 times 10 to the minus 7. And when I'm put that together, I get this number. So when we make our comparison, we have a Ksp to equal 2.3 times 10 to the minus 9 against a Ksp to equal 2.5 times 10 to the minus 9, and we see that the Ksp is greater than the Ksp. So the inequality right here tells you the direction is going to shift. It's going to shift back to the left toward the solid. And yes, the answer is yes, precipitation occurs if you mix those ion concentrations together. So you take what they've given you, plug it into the Ksp expression, get a number, and then compare it to the Ksp value. They have to give you that, whoever they are.
If,
I won't move it.
I have a question. Can you speak up?
This indicates the system will precipitate or shift back in that direction.
Yeah.
If we had gotten, say, a 1.8 here, hypothetically, then it would have been the other way around. This would shift to the right. The Ksp is greater than the Q. Shifts to the ion side. So that means you not at saturation. It means ions are still going into solution. If you have one going to the left, it means solids coming out of solution. If it's equal, you're at equilibrium. If here, that means you're saturation. That's what it's called. Saturation. Right there. Real quick. Calculate the pH of a solution, saturated solution of iron hydroxide. We'll give you that. Ksp equals iron which is x times 2x, just stringing it out for you, 4x cubed. So x is equal to the cube root of Ksp over 4, cube root of 8 times 10 to the minus 16 over 4 molar. That's the solubility of X right here, but the hydroxide concentration is 2X, which is 2 times 10 to the minus 6 molar. 1.17 times 10 to the minus 5 molar. POH is equal to the minus log of the hydroxide concentration, 4.93, and pH is equal to 14 minus 4.93, 9.07. Almost made it. Yeah, I made it. Pretty close.